problem is related with the heating. This is the disc insulator. The insulator consists of the metal cap, the porcelain body, and the clamp. And the insulator could be connected one after another in chain. You know, the transmission line are built in the open air, so there are humid, there are some pollution in the air that produces the thin conducting layer on the insulator surface. And the fault could occur, the current will carry through the conducting layer. Our task is to calculate the temperature. The flowing current will generate some power losses. We will calculate the leakage current. And the insulator temperature. To calculate the temperature, I will simulate two problems. In electric problem, I will calculate the leakage current and the losses. And in the heat transfer problem, I will calculate the temperature. So let's take a look at the geometry model. This is the cross-section of the insulator. The model class is axisymmetric. That means that we have the rotational symmetry, and the horizontal axis is the rotation axis. The alternating voltage is applied to the clamp, and other part is connected to the transmission line tower. So this part has zero potential, and this part has high voltage potential. The frequency is 50 Hz, and we need to calculate the current that flows in the thin layer of the dirty on the insulator surface. So we have the porcelain insulator with very low electric conductivity, and we have the thin layer of dirty with high electric conductivity. So let's imagine some rainy day. There is water on the surface of the insulator, and the water is not pure water, it's a conductor. And we need to calculate the leakage current through this water layer. This is the grounded part with zero voltage, and this is the high voltage part, 10 kilovolts voltage. You know, it is required about 10 insulators for transmission line of 110,000 kilovolts, so it's about 10 kilovolts per one insulator. Now let's take a look at the simulation result. This is the electric field lines, and I'm interested in the currents. So I will switch on the current density. There is almost no current in the insulator body, but there is current in the small layer of water on the insulator surface. This is how the current flows. And of course, this current produces some joule heat. So I select the layer and I will calculate the active power produced in the volume. About 15 watts produced in the thin layer of the water on the insulator surface. Now let's calculate the temperature. To calculate the temperature, I will simulate the heat transfer problem. So this is the heat transfer problem, the same geometry model. In heat transfer problem, I should specify thermal properties for each object. I specify thermal conductivity of the porcelain, and I should specify the volume power generated. There is a way in QuickField that you can transfer the calculation results from one problem to another problem. We call it coupling. As the power losses are not distributed uniformly in the layer, I cannot simply put 15 watts in thermal problem. I would like to import the power distribution from electric problem. So in my heat transfer problem, I create the link to the electric problem. From electric problem, I will import the generated heat, and the temperature will be calculated based on this generated heat. So again, the rainy day, humid air, some current flowing on the surface of the insulator. The temperature outside is only 10 degrees Celsius. Now let's take a look. Now let's calculate the insulator temperature. The insulator is heated by the leakage current. So you can see the insulator temperature is about 25 degrees Celsius, and the air temperature is 10 Celsius.